conference leader unmute your line.
So I should be able to hear all the speakers now. We will have the Q&A period will be at the end, so we'll wait for everybody at the end of the webinar, probably with about 10 minutes to spare before 3 o'clock Eastern, so that we can answer folks' questions that they've typed into the Q&A tab at that time.
I'm assuming you can still hear me, Dave?
Yes, I can.
Okay.
So our agenda is up on the slide right now that everybody should be able to see. So Ron Grady from HDR will be giving an introduction to pump storage and renewable energy. That'll be followed by a discussion on generating equipment from Julius Kurachik at HDR. And then Pat Wazlowski from Lewis Berger will be talking about the licensing process. Then Andy Johansson from Alden will talk about pump storage hydraulics, and we'll finish with Steve Amaral from Alden talking about fish protection consideration. So with that, I'll move on to introducing Ron Grady. He's a professional civil engineer employed by HDR with over 30 years of experience dedicated to the pump storage, conventional hydropower industry, including siting and feasibility studies, detailed design, field support during construction, as well as operational and maintenance support. He's currently Vice President and responsible for providing project management and engineering and technical services for major projects, both domestic and international. Most recently, he's been engaged in numerous pump storage projects at various stages of development. And with that, Ron, I'll turn the floor over to you.
Okay, thanks, Dave, and I appreciate the opportunity. Dave asked me to provide a brief introduction to pump storage, as well as maybe some information to really determine the economic feasibility of pump storage. So I've provided some slides, and I'll go through those. This is going to be a fairly high-flying presentation, so I apologize if all of your details don't get addressed. But really one of the challenges, at least in the U.S. and in many other developing countries, are challenges associated with balancing the transmission systems. And that really includes balancing supply and demand, following short, medium, and long-term variation in load, actually load following with flexible and dispatchable resources, and then accommodating large net load ramping events that are becoming more common, particularly with the influx of renewable energy resources. Some of the solutions that we feel like grid scale storage can provide. It can enable, and is proven that can enable double-digit levels of wind penetration, which is becoming quite a challenge in some areas, particularly in the Pacific Northwest of the U.S. A good example is in Europe, where they integrate a lot of their variable energy renewable resources with big transmission and conventional hydro and pump storage. We see a changing U.S. market for system reserves and grid reliability that we feel like pump storage can also play a role. We have to, if we're going to talk pump storage and transmission challenges, we have to certainly discuss the wind integration. Certainly, wind has become an increasing source of intermittent renewable energy resources, and we all know that the wind generation can change suddenly. We know that wind generation often occurs during off-peak periods, and we know that this can lead to transmission congestion and wind output curtailments. Give you as an example, in Denmark, they have about 30% wind penetration. They have no native load balancing, and really their balancing services are provided via transmission interconnects with Norway, Sweden, and Germany. And what happens is the wind, when the wind picks up, this intermittent renewable wind is then transmitted to these countries and stored really with the large hydro fleet and the large storage reservoirs. For example, this is a figure, and it's a bit dated in January of '07, but it clearly shows the wind output is directly proportional to the net power flow, and that net power flow is actually transmission flow going to the neighboring countries for storage. This is kind of an interesting figure. This is actually BPA system. Again, this is in December of '07. What this figure shows, I think, is that in periods of peak demand, particularly here in the December 27th of '07, you had a drop in demand, which actually is at the same period of time where you had maximum wind generation. So, and you can see that at this particular time, there was about 1,000 megawatts of wind, and it's a kind of a very daily cyclic event. This next figure, let's move ahead to 2012. Again, this is on the BPA system, and you can see the wind, instead of 1,000 megawatts now, is 3,000 megawatts. And you can see that the wind load in megawatts is being absorbed by hydro. So during low wind, you've got your maximum hydro generation, and at your peak wind, you've got your low hydropower generation. So really, hydro along the BPA system is balancing wind at this particular time. I know there's some concerns about the influx of additional renewable energies and the impacts on their system. Why energy storage? Attenuates generation volatility. It can align peak generation with peak loads, reduces imbalances in the system, moderates transmission congestion, and enables further penetration of variable renewable resources. This is kind of an interesting figure that shows bulk storage technologies. On the left, the figure actually shows log, and you can see pump storage in this little circle to the right. But if you do a linear figure, then the pump storage plays much more of a role, particularly for grid storage. This is just a little plug for pump storage. What is pump storage? Really, it's like a battery, and it's an efficient means to store energy when the power demand is low, and then provide energy when the power demand is high. And it simply works by moving water from an upper reservoir to a lower reservoir when you need power, and vice versa when you have excess power. Here's just some alternative project profiles for pump storage. You can look at this at a later date, but it's various underground powerhouses versus shoreline powerhouses, horizontal intakes versus vertical intakes, etc. This is just another definition of a plan and profile for a pump storage. You can see the upper reservoir on the left and the lower reservoir on the right, and then you have your water conveyance and power complex in between. 3 modes of turbine operations, and I know Julius is going to get into this a bit more, but just from a very simplistic standpoint, You got kilowatts out, you got water rotating the turbines, generating power. In a pumping operation, you reverse and you're pumping, and you actually got power in, and then you can operate in the synchronous condensed mode, sync to the grid for rapid response. This is just kind of a schedule that we've utilized for various pump storage studies. You've got various study phases from a recon to a pre-feasibility to a feasibility, and these have varying degrees of cost and detail that are produced. And as you move from recon to feasibility, the level of accuracy in your studies and your cost basis tighten considerably. This also indicates, shows initial design and some of your tender processes, final design, and then your regulatory phase, and this actually shows the ILP process. The point is, these aren't developed and realized in a month, in a year. It takes many years from start to finish, depending on how aggressive your investment program is and how much risk you're willing to accept. Some of the considerations for evaluating pump storage, first of all, it really helps to have favorable market conditions. In other words, if you have an ancillary market, or you have the ability to establish power purchase agreements or power sales agreements, power pumping agreements, you're way better off. Of course, you need favorable geology. You need favorable environmental and regulatory settings. Obviously, you need topographic features that maximize operating head and minimize the water conductor length. You need to have two reservoirs that are within the operating range of the units. You need to consider unit submergence, particularly if you're looking at below ground powerhouses versus shoreline type powerhouses. If you have existing infrastructure, that is a huge plus, particularly transmission and roads. There's a lot of discussion going on now about closed loop versus open loop systems. Closed loop would be where you have a dedicated upper reservoir and a dedicated lower reservoir that don't really have any impact to existing waterways or reservoirs. From an environmental perspective, closed loop is much more acceptable. From an environmental and regulatory perspective, you need available construction materials, and you need adequate overburden over your tunnels. Some of the equipment and layout considerations that are taken into account during the evaluation phase, obviously, your underground versus shoreline, and really that is an economic decision more than anything. Operational objectives and desired performance. In other words, how are these projects going to be operated? How can you best make money from these pump storage facilities? How aggressive are the water columns going to be jerked around? What type of run times do you need? What type of services are you going to be providing to the market? What kind of transients are set up in the system, et cetera? Another item of consideration is single speed versus variable speed. Most of the pump storage facilities in the U.S. That were developed prior to 1991 are single speed technology. We're seeing a push to variable speed, particularly because of the need for regulating in the pump mode. It offers much more flexibility, and again, Julius will be addressing that. Selecting the number of units, obviously the more units, the more smaller units you have, the higher the cost. The less larger units, the less the cost. Optimizing speed, again, this as it relates also to settings, it does impact cost, construction costs, unit sizes, etc. Transient analysis always has to be considered as it relates to the design of the facility, and then powerhouse sizing considerations as well. Underground transformers, above ground transformers, things of that nature. Operational characteristics, these are just some of the things pumped storage can offer. For example, standstill to full generation in less than 3 minutes, 100% pumping to 100% generation, 6 to 10 minutes. Again, these operating characteristics would be identified in the early design phases of the project, and then the tunnels and water conveyance systems and units designed accordingly. 100% pumping, 100% generating, 100% pumping in 6 to 10 minutes. Of course, load following capabilities, et cetera. So the last bullet here is variable speed technologies are available and offer significant greater benefit, but they, again, have an incremental, they cost more than single speed, they require a bigger powerhouse, et cetera, and we can talk a little bit about that. Advantages of single speed and variable speed. Single speed pump turbine technology, it has a lower cost component. It requires a smaller powerhouse, and it has ever so slightly O&M cost. Variable speed has a wider head range operation, flatter and higher generating performance curves. Again, it can regulate in the pumping mode. It has a wider generating operating range. So with that, I'd like to turn the presentation over to Julius, who is going to provide some additional information regarding pump storage units.
And I'll jump in here with some quick background on Julius. So Dr. Julius Gurechik has over 30 years of experience in working with leading manufacturers of hydraulic turbines and pump turbines. He currently holds a position of senior consultant with HDR Engineering. And as Ron mentioned, Julius will be talking to us about generating equipment. Go ahead, Julius.
Thank you, Dave. I hope I'm heard. No,
yeah, we can hear you fine.
But I'm having difficulties switching slides.
I can switch for you if you need. It's the arrows in the lower left-hand corner that you need to use.
That doesn't seem to work for me. Sorry for that.
Okay, I'll go ahead and move to your...
please, yeah, thank you. Okay. So we have over 100 pump storage generating units in the U.S., and most of them are dating from the 1960s and the 70s, and despite modernizations done recently, they are still representing that technical level. So in the meantime, the industry has gained quite a bit of experience. Also, there is, especially in the recent years, proliferation of computational methods that make the product much more attractive. But the most exciting development is variable speed, about which Ron has mentioned. Next, please. The primary reason for variable speed pump storage is this is an economically attractive way of controlling grid frequency, and this happens on two different time scales. In the long time scales, minutes and hours, we can regulate pumping power. Obviously, in the generating mode, we can regulate regardless if this is single speed or variable speed. But what is also very important, especially with the influx of renewable power and stable power, is the short time scale regulation, which happens in a matter of seconds or even fractions of a second, when the inertia of the rotating parts could be used to store energy. By changing speed upwards or downwards, we can absorb or release power in a very short time period. The obvious drawback is higher equipment costs. So it's typically about 30% of the cost of the equipment itself. Next, please. Shortly about power regulation in pumping. the constant speed pump turbines can only pump with a given power. It changes a little bit with the head, but there is no possibility of changing that. The variable speed pump allows to vary the input in a quite wide range. That's the blue box on the graph. Typically, it goes down to 60% of the rated capacity. Next slide, please. In the generating mode, the primary advantage is much wider operating range, while for constant speed, as the graph on the right shows, the lower end of the adjustments of the power is about 50% or so of the rated capacity. Variable speed pump turbines can go down even below 20% by selecting the proper conditions through the right speed. There is also a slight gain in the efficiency for better operating points, but this is not a substantial difference. It's at most perhaps 2% or so. Next, please. What does it mean for the equipment? The pump turbines practically are the same as for constant speed. There's no difference there. All the weight is in the electrical part, and the most limiting part there is the power electronics that allows the variable speed to happen. It is very expensive on one side. There are limits in terms of capacity and the voltage and so on. So the solution widely used in power generation is using the AC excitation. So the principle is that the magnetic field of the stator rotates with the frequency of the grid, while we can control the through AC excitation the frequency of current in the rotor. And this way we can change the speed in not in a wide range, about 4 to 8% typically, but this is enough to allow pumping with in different conditions. But this way also we can limit the converter capacity to about typically 10% of the motor generator rating. So the cost of this could be reasonable. And the image on the right compares a synchronous unit of a single speed on the left and a variable speed on the right, which has quite a bit of difference in terms of the rotor construction, which resembles rather the stator of a conventional generator. Next, please. This is not a new technology any longer. It exists for over 20 years, with the first unit started in 1990. So it's a time-proven method. And right now we have several dozens of units, pump storage units over the world, with a maximum capacity about 400 MVA. And another 15 or so under construction, mostly in Europe, Japan, and even in India recently, with a maximum capacity close to 500 MVA. Next, please. So in summary, if it comes to construction of new plants right now in the U.S., we have the option of a single speed, which is a time-proven method, very well established, and offers lower cost, especially for the equipment, or the variable speed, which provides a possibility of balancing the effects of large-scale wind and solar generation. So thank you very much. That's my part.
Thanks very much, Julius. And I'll also just remind folks that for questions, please feel free to log questions in the Q&A tab in the upper part of your live meeting interface, and we'll address those questions, as many as we can, at the end of everybody's presentation, or at the end of all the presentations. So next, I'll introduce Pat Wysłowski, who's going to talk to us about the licensing process. She's the Director of Hydropower Services at the Lewis Berger Group. She has broad experience in the fields of management and historic preservation, spanning 38 years, including positions in public, nonprofit, academic, and corporate settings. In particular, her experience includes more than 18 years in a corporate environment preparing National Environmental Policy Act documents and more recently managing Louis Berger's third contract providing hydroelectric and environmental engineering support services to the Federal Energy Regulatory Commission, or the FERC. Pat?
Thank you. Ron mentioned in his presentation, he illustrated a regulatory process that would take up to 5 years, and I'm going to be focused on that regulatory process, which is required to get a license from the Federal Energy Regulatory Commission, otherwise known as FERC. I'm going to focus on some strategic decisions, stakeholder consultation, and some steps to help manage the timeframes and costs. The regulations for licensing conventional and pumped storage projects are found on the FERC website at ferc.gov Industries Hydropower, along with copies of the flow charts that you'll see in my presentation, and other very helpful guidance to help you navigate through the licensing process. There are two major stages. One is the pre-filing stage, and the second is the post-filing stage. In the pre-filing stage, you're going to start with a preliminary permit. I suspect many of you have them if you're involved in putting together projects now. That preliminary permit gives you a 3-year window to assess the feasibility of placing your project at a particular location, and it holds that location during your analysis. You conduct some stakeholder consultation, and ultimately you prepare a pre-application document and notice of intent, and that's your first key filing with the FERC. You can also get a successive permit that currently would allow 3 more years. That's issued based on the adequacy of your progress reports and on meeting your filing deadlines. The preliminary permit process really ends with the pre-application document. That's a document that sets out the readily available information, your baseline information, what the site's all about, what your project's all about, how you're going to operate it. You may decide to do some limited studies to augment existing information if you feel you know your stakeholders' interests. You may want to include study plans in your PAD document. You will hold stakeholder meetings. And key, you need to make a strategic decision as to which process you're going to use for your application. I'm assuming that most pumped storage projects, because they entail a considerable amount of construction generally, will use the default integrated licensing process. There are 2 other processes available, a traditional process and an alternative process. The integrated licensing process allows you to do your scoping and determine what studies you're going to do before you file your license application. This is a flow chart of the pre-filing activity. You may not be able to read all of it, but there are regulatory citations and time frames for each of the steps. This flow chart is available on the FERC website. The pre-filing steps involve FERC issuing a scoping document, what are the issues, and conducting scoping meetings to solicit stakeholder comments on the project. FERC, as well as stakeholders, will comment on your pre-application document, your scoping document, and your study request. And based on all of that feedback, the applicant prepares a proposed study plan. That goes out for comment. Based on those comments and stakeholder meetings, the applicant prepares a revised study plan. And with all of that information available to the agency, FERC then issues a study plan determination. That study plan determination tells you what studies you need to do and the methodologies you need to follow and the time frames that you have to conduct them in. There are processes for dispute resolution in these guidelines, so I'm not really going to focus on those right now. You then conduct your field studies. Once those studies are done or mostly complete, you put together a preliminary licensing proposal. That document includes exhibits that describe the project, Exhibit A that describe the operations, Exhibit B that describe the construction schedule if applicable, Exhibit C, cost in Exhibit D, and your environmental impacts in Exhibit E. You can also file a draft license application instead of a preliminary licensing proposal, and that document would include your Exhibit F, your drawings and plans, and your Exhibit G, your project boundaries and land ownership in the project area. And of course, you have stakeholder consultation at that stage as well. Once FERC comments back on the draft license application, you prepare a final license application, and there are time frames for all of these steps in the regulations and in the flow charts. Your pre-filing activity concludes with your filing of a final license application. At that point, FERC will look at the application for adequacy, will determine whether or not you've provided all the information required by the regulations, and if you haven't, they'll issue a deficiency letter, or they may issue an additional information request if your information is not clear or if there are inconsistencies in your documents. Once you've provided all of the information that the FERC has requested and solved any of your deficiencies, then FERC will issue an acceptance notice. They may issue a ready for environmental analysis notice at the same time, and they'll request final terms and conditions from the agencies. That's about a 2-month process, and once the final terms and conditions deadline has passed, FERC will then put together its NEPA documents, either a single document or a draft and final. I think for pump storage facilities, typically there would be a draft and final document. The final step that FERC takes is to issue a license, but it cannot issue a license until there's been a water quality certification issued, and for closed loop pump storage systems that may not be required. It cannot issue a license until any biological opinions have been issued, if there are threatened or endangered species that might be affected by your project, and you're in the process of consultation on that. And FERC cannot issue a license if there are historic properties affected and a programmatic agreement with the state historic preservation officers required. So you may get through all of the pre-filing, filing, and NEPA review, but then you may well find considerable delays if these 3 items aren't addressed. Your strategic decisions are at the initial stage in determining which process to use. The ILP process does your scoping up front and gives you a more definitive answer as to what studies you'll need to do. The traditional process does the scoping after filing and is more open-ended relative to the possibility of additional studies being asked. You need to decide whether you're going to do other studies before you put your pad together, and whether you're going to put study plans in that pad, and then the degree of candor in the filings. And by that I really mean the way in which you assess the impacts. Are you providing a realistic assessment of the impacts of your project on environmental resources? The stakeholder consultation piece of this really needs to reflect due diligence in identifying your stakeholder groups and the tribes that might be affected or interested in the project area. You need to present real opportunities to review and comment, and you need to adhere to the rigid timeframes in the ILP process. And those timeframes can be very intense. So it's important that you have developed good stakeholder consultation procedures. Some steps or suggestions to help manage, help you navigate through this process as quickly as you can, because time is money and presumably you want to get your project under construction. Consult early and often with both FERC and your stakeholders. Consider the appropriate seasons for protocol and other studies. If you can construct your schedule in a way that you can accomplish your studies in one field season, that's obviously going to be more advantageous for you. Use FERC's environmental assessment and environmental impact guidance documents when you put together your Exhibit E. It's a very helpful resource. Strive for internal consistency between your study reports and your license applications. And finally, be thorough to avoid time-consuming additional informational requests, because they could add 3, 4, 5, 6 months to your processing time. So that's how the process currently works. I know there's legislation working its way through Congress that might require FERC to study the feasibility of reducing or streamlining the process for pump storage licensing to a 2-year process, including both pre-filing and post-filing, but that's a little ways off. And that's my advice.
Thanks very, very much, Pat. Appreciate that talk. Before we move on to the next presentation, I know there was one question that came up about getting slides, and we will be making PDFs of all the slides and hopefully a recording available to everybody who registered. So you should be getting an email about where to download those from. I'll move on to the next presenter then, Andy Johansson from Alden. Andy is Alden's Director of Hydraulic Modeling and Consulting Services. He has over 25 years of experience in modeling of pump and turbine intakes, and he's going to be talking to us about pump storage hydraulics. Andy?
Thanks, Dave. Again, as Dave mentioned, I'll be having a brief discussion today on pump storage hydraulics. Some of the areas that we'll be focusing on is, where are the hydraulics of interest? And some of those locations include lower reservoir or supply body of water, the upper reservoir in a pump storage project, the pump turbines, and the flow conveyance system, whether that be tunnels, shafts, penstocks, draft tubes, bifurcations, etc. Why would you want to look at the hydraulics associated with a pump storage project? Certainly if it's a new facility, the hydraulics would be of interest. You want to ensure that the hydraulics are going to be sufficient and minimize operation and maintenance expenses over the duration of the project. Possibly there's been site changes over time. Site changes could include decrease in reservoir water level, or perhaps a change in the bathymetry at a particular site that could be impacting hydraulics. Perhaps there's been an increased capacity or potentially looking into increasing capacity. And so how would that increase in capacity affect the hydraulics at an existing pump storage project? And again, as I already mentioned, changes in expected water levels. So what tools do we have available to us to evaluate pump storage hydraulics? A couple of the tools that we do have available to us include accurate physical and computational fluid dynamics modeling. With these tools, we can confirm performance of pump turbines. We can provide information on how changes will impact the hydraulics, and we can also use these tools to develop modifications to mitigate long-term operational and maintenance concerns. Again, we have a couple different options. We have computational fluid dynamics modeling or numeric modeling. These do have cost and schedule advantages over physical models, And typically, once the simulations are conducted in a computational fluid dynamics model, more information is readily available. Physical models, they are still able to predict some phenomena that CFD is not capable of simulating. That includes highly swirling flows such as with vortexing and vortex activity. So again, now I'll move forward and discuss a little bit some of the hydraulic phenomena of interest. Some of these I've mentioned already. I'll go into a little more detail here. Vortex formation, again, this can occur in both the lower and upper reservoirs at the intake structures themselves. Vortex types can really vary from a very weak surface swirl to a much stronger vortex, which could potentially pull in floating trash or even air into the pump turbines themselves. The adverse vortex activity can result in unacceptable hydraulics and air entrainment, impacting flow, head, power, cavitation, increased vibration, and noise. So with the use of these tools, we can determine whether or not any adverse vortex activity is present, and if there is, we can develop modifications to mitigate the vortex activity. Some additional phenomena of interest would be velocity distribution and swirl at the pump turbines themselves. Pump turbines are usually designed with a nice uniform approach flow in mind and tangential flow or axial flow rather. If there is a tangential component to it, you have a swirl in the flow, and that can impact the possible performance of the pump turbine. Again, we can, with both types of models, we can look at swirl and velocity non-uniformity, which can change performance characteristics and cause uneven loading of rotating elements. And again, use these tools to mitigate and come up with modifications to minimize any swirling flow or non-uniform distributions. Head loss may also be of interest. Increased head loss can impact the efficiency. These head losses can occur at different locations. They can occur at the intake and discharge structure. They can occur within the tunnels, shafts, penstock, draft tubes, and bifurcations associated with the project. And through the use of the various types of models, we can determine exactly what those losses are and modify designs to minimize those losses. Scour, sedimentation, and debris. This may also be something that's of interest. This can occur in both the lower and upper reservoirs. We can use modeling or models to look at bed shear stress and velocities, both along, say, shorelines and along the bed, and determine whether or not adequate riprap protection is available, or whether or not the riprap protected area needs to be extended. Obviously, this can impact O&M costs and safety, and certainly something that should be avoided. So to conclude, we have accurate hydraulic models can be very useful tools to evaluate hydraulic phenomena at pump storage facilities. The tools include physical models, numeric models, and combined physical numeric modeling approaches. The tools can be used to provide information on how changes will impact hydraulics. These may include changes that have occurred over time or operational changes, say increased flow capacity or water level. And then lastly, if we find that there are adverse hydraulic conditions or hydraulic phenomena, these tools can be used to develop modifications to mitigate long-term operational and maintenance concerns.
Great. Thanks very much, Andy. And before I move on to Steve Amaril's talk on fish considerations, I wanted to remind people that as you're listening to these presentations, if you have any questions, please go ahead and enter your questions in the Q&A tab at the top of your live meeting interface, because we do anticipate having a few minutes for questions at the end. So as I mentioned, Steve Amaral will talk to us about fish protection considerations. Steve is a senior fisheries biologist at Alden. He has extensive experience in the assessment and resolution of fish passage and protection issues at all types of water intakes. He manages laboratory and field evaluations of developing and existing fish passage technologies, and he performs evaluations of aquatic resource impacts for hydroelectric project relicensing and for meeting the Clean Water Act Section 316B requirements. He was the lead author in the development of a guideline document for hydroturbine entrainment and survival studies. Steve?
Thanks, Dave. And I just want to thank Dave for picking a picture that's about 15 years old, where I have a lot more hair and a lot less gray in my beard. Okay, today I'm going to talk a little bit about fish protection at pump storage projects. It's sort of a 30,000-foot view of some of the issues that have to be addressed and the mitigation alternatives. Certainly there's a lot more details that have to be investigated as folks license new projects or relicense existing ones. But the major issue is fish that are in the vicinity of upper and lower reservoir intakes may be subject to entrainment through the turbines or pumps, or possibly impingement on trash racks. The next three bullets I'm going to talk in more detail after this slide, but they include the risk of entrainment impingement, which will depend on certain project design and operational features, certainly environmental and hydraulic conditions and how they influence fish behavior and movements, biological factors related to species, size of fish or life stages, and then various movement patterns, whether fish are resident or migratory. Some of the potential impacts that can result from entrainment and impingement, they'll depend on the magnitude of losses, and these can include losses from one reservoir to the other, just by losing, it could be live fish being lost from a population, or it could be mortality through the pumps or turbines, and then there could possibly be migration delays. It'll also depend on existing population levels, whether the species present is a healthy or depressed population, potential impacts for what are threatened or endangered species, and then life history, strategy, and biology of species of interest. And again, this would be a more resident or local species versus one that is a obligatory migrant, like an anadromous or catadromous fish. And then I'll talk some about the mitigation technologies that are available to reduce entrainment or impingement, and these include different fish protection systems and potentially modifications in project operation. So entrainment and impingement risk is going to depend on several things. Certainly the type of water body used for both the upper and lower reservoirs. Often the upper reservoir is a man-made impoundment. The lower reservoirs can be rivers, often impoundments to a more conventional hydro facility with a dam. Could be natural lakes, or it could also be a man-made reservoir. This will influence the type of fish that are present in the vicinity of the intakes. Certainly intake location and design with respect to the depth, the bar rack spacing, and other aspects will influence whether you can have high or low entrainment or impingement rates. Intake approach velocities and hydraulic zone of influence, whether or not fish encounter the intake, what's the probability, and then if they do, what's their ability to avoid entrainment and impingement. Certain environmental factors like water temperature and turbidity will influence fish behavior and their ability to stay away from the intake. Fish size and swimming capabilities, if they do encounter the intake, will influence their ability to escape. And then diel activity and migration behaviors. There are species that will migrate during certain periods of the day or are more active during certain periods of the day, and this will influence their exposure to entrainment and impingement. The potential impacts, again, with transfer of fish from one reservoir to another. Typically, if you're losing fish from the lower reservoir and it's a natural river system or a lake, it may not be desirable to have them transferred to the upper reservoir where often there isn't any public access due to the large changes in water elevations. There can be loss of fish both during pumping or generation due to mortality for passing through the pump turbines. There can be mortality from impingement on bar racks as influenced by the approach velocity and the spacing of the rack. And then if fish are transferred up into a reservoir during their migration past the facility, they could be lost to the migration or delayed and would have to go back down through the turbines in order to continue. Some of the alternatives for mitigating potential impacts include fish protection systems that are designed to reduce entrainment impingement. These can be narrow-spaced bar racks, screening systems, barrier nets are also a possibility. Behavioral deterrents like sound, strobe lights, air bubble curtains have been investigated in the past. There can be modified project operations, so reduced pumping at night or reduced generation during the day, depending on where you're trying to reduce entrainment. Multi-year performance monitoring typically is required if there is some kind of system installed, and often it's going to involve a series of studies that result in modifications in the system until you achieve performance levels or effectiveness levels that are acceptable to the resource agencies. I'm going to go through several sort of case studies at this point, just 4 sites, and focus on the box, which covers some of the biological issues at each one. You can see above it there is some information on the design and operation of the project, but these have all had to address fish issues at some point. They are existing projects, and a couple of them are going through relicensing now. The first one is Northfield Mountain. This is located on the Connecticut River in Massachusetts, and we can see the flow in the Connecticut here. We can see the flow in the Connecticut here. This is the intake, the powerhouse of the pump turbines, and then the upper reservoir. The primary issue here is smolts migrating downstream past the intake and being entrained during their out-migration. What they did here was install a guide net. This is from a Google image. You can kind of see this net here. I'm not sure if it's in the exact place it is normally when it's in protection mode. This is a boat barrier. Here the velocities are lower. One concern, though, is when there's a lot of generation flow that the direction and magnitude of the velocities can carry fish through. But they put this out seasonally during the smolt migration from April 1st to June 15th, depending on flows and their ability to put it in. It's about 650 feet long with a 3/4-inch square mesh. During the migration, they also limit pumping to 3 units or less to help reduce velocities in the flow direction along the net. And testing over time, the last results I was able to find was that it was about 93.3% effective in guiding tagged smolts away from the intake. They did record some minor impingement numbers for untagged fish that were naturally migrating from upstream on the net. But for the most part, I think the agencies have been happy with the performance. I should note that the salmon program here for restoration of salmon has been ended, so they'll have to continue to use the net until 2015, after which they don't expect any more migration of smolt in the river. The next one is Ludington, probably one of the biggest pump storage facilities in the U.S. You can see in the top picture the upper reservoir with the intake on Lake Michigan below. And then barely visible, there is a 2.5-mile barrier net that's been installed to keep out forage and sport fish, generally greater than 5 inches in length. They do put this out seasonally as well, from April to October, and they've done extensive studies here And for all the target species combined, it has been over 95% effective, and I think everybody's been very happy with the performance of this technology as well. Richard B. Russell, a little different than the other projects. This is on the Savannah River. The upper impoundment is Richard B. Russell Lake, which is impounded by the dam you see here in the picture. And below it is the impoundment for J. Strom Thurmond Dam. And they do pump back and generate through Richard B. Russell. And the primary issue is entrainment of lower reservoir fish during the pump back operations. In particular, they were getting large numbers of blueback herring entrained and killed during pump back. They come up with a combined system of a sound deterrent for blueback herring, ultrasonic frequencies. They use overhead lighting along the shorelines to attract fish away from the intakes, which are located here. And they also have put in a rock berm, which I'm not sure if it's visible, but it helped reduce some hydraulic conditions that attracted fish to areas near the intake. And there are pumping restrictions as well during certain times of the year and certain periods of the day to help minimize entrainment rates. I couldn't find any hard numbers on the effectiveness, but again, I think they show good reductions in entrainment, and everybody's been happy with the performance of the combined system so far. One more to go through here, and this is Muddy Run on the Susquehanna River in Pennsylvania, and it's upstream of the Conowingo project that withdraws water from the Conowingo impoundment. They actually do not have any fish protection systems here, but there was a lot of studies done back in the late 60s and early 70s as the project was constructed and became online. For the most part, they concluded that there weren't any major impacts to the primary fish species of interest. So there's no specific measures were implemented to reduce entrainment. They are going through relicensing now, and I know there's a lot of studies going on for migratory fish movements, including American shad and American eel. So that's all I had today. I just wanted to end with some references for the various sites I just talked about, and these cover some good information that covers some of the issues that have been evaluated in the past.
Great. Thanks a lot, Steve. So just as folks, I know we're running a little bit over time here, but if people can stay on a few extra minutes, we can answer some questions. And so as you're thinking about your questions, we just have a summary here of, first we had sort of an overall introduction on pump storage and renewable energy from Ron Grady. Julius talked about generating equipment, especially variable speed versus fixed. And then Pat talked about the licensing process. Andy talked about pump storage hydraulics, and then we just heard Steve talk about fish protection considerations. I'm going to leave this slide up here in terms of everybody's email addresses, so folks should feel free to copy those down if you have additional questions for the speakers. Some questions that came up, let's see, there's a question here that says, in terms of size, is there a limit for small-sized pumped hydros? For example, installation smaller than 1 megawatt. This could be the case for small islands where they want to reduce dependency on fuels such as diesel. What are the typical costs of pumped hydros in terms of dollars per kilowatt and the operation and maintenance yearly costs? So I think, Ron, you're probably the best person to take that one.
Yeah, thanks, Dave. And what we have seen is we've looked at a lot of the cost for existing pump storage, and they tend to, the cost of the developed assets tend to range at about $2,000 a kilowatt, plus or minus, 30, 40% each way. Now, what does that mean? Obviously, for small small pump storage in a captive market, like I think they had some successes on the Canary Islands. But really, when you look at the value of pump storage and the cost of pump storage, generally speaking, the the greater amount of head, the smaller water conveyance system, the more economical pump storage will be. Also, that taken into account, there are certain economies of scale. The larger projects tend to cost less on a dollars per megawatt basis. So I think there is some precedent for some small pump storage. I don't think there's a lot of precedent at the moment, unless you have a very isolated situation, like perhaps in the Canary Islands. O&M cost, there are formulas for O&M cost. I know EPRI produced a document several years ago, pump storage guide document, and it has typical O&M cost, annual O&M cost, and it's a function of capacity and energy. Also, there are costs associated with major maintenance, particularly after 20 years of service, depending again on the operation. So, if somebody wants to contact me directly, I can, give them much more detail.
Okay, great. So another question that came up, and this is probably best for Julius. What's the overall cycle efficiency of pump storage with variable speed and with single speed units?
There's not much difference in terms of the efficiency between the single and the variable speed. And for the equipment itself, it's in the 80s to 80 to 85%, but this is the equipment only. But for the real assessment, we have to consider also the water conveyance, all the losses in the hydraulic conduit, and that obviously changes from case to case, and typically is within 70 to 80%. That's the best I can say.
Julius, we're seeing toward the upper end of that for most of the projects we've looked at for cycle efficiency.
Thank you.
78 to 80.
Okay, great. And then I think there's a follow-up question here for Ron. So what are the average capital costs for a megawatt of projects in the 100 megawatt plus range using existing lakes as upper and lower reservoirs?
Pump storage, each one of them is so site independent. Again, I would just have to check back to the global numbers out there, and I would say if on average you're at $2 million a megawatt, and then you have existing reservoirs, I would say you would be again on the lower end of that, maybe $1,500 a kilowatt or $1.5 million a megawatt. But again, this is such at a high level. Everything is so much site specific that it's hard to say. But I would tend to say they will be on the lower end of the average.
Okay, great. Thank you, Ron. Another really interesting question that almost everybody might want to touch on here is a question about pump storage with seawater, and are there any special issues? I would think, Pat, maybe you might want to start with that in terms of licensing.
Seawater issues?
Yes.
So you're talking about salination?
Well,
maybe,
or, pumping seawater up to an upper reservoir, I presume.
Mm-hmm. I would think the issue there would be more on the equipment.
Yeah, I didn't know if also in terms of, leaching issues, pumping seawater up to an upper reservoir, whether that might have some groundwater impacts.
Might depend on whether they're using a liner or not using a liner.
Right.
If I may add, there is an existing power plant in Japan, in Okinawa, Yanbaru, rated about 30 megawatt with a single unit, operating since, if I remember, mid to late 1990s. It's a good experience. Of course, it had to go through certain things to assure no corrosion and no seepage and so on. But the owners claim that this is a very good project, so it is certainly feasible. I would like to add that there is also pump storage of a different kind. This is Larance pump storage in France with 24 bulb units that are able to pump seawater back and forth, in operation since the 1960s, and this is a success. So with proper corrosion protection works.
Okay, great. I don't know, Steve, do you have any thoughts on seawater in terms of fish?
Probably the same issues with the river or lake. If it was in a sensitive area, some coastal areas can be very sensitive as far as fish populations and types of habitat. So they would have to address the same issues I think they would anywhere.
Okay. Another question here is what examples are there for both reservoirs being upstream? So I think this would be like a closed loop system. And obviously I would think, Steve, you basically take the fish issue out of the picture, right, when you do a closed loop system.
If they were man-made or, impoundments that weren't accessible to the public, then there probably wouldn't be any major fish issues. Right.
Pat, do you have any comments on that?
Well, one example that's current, the Eagle Mountain Pump Storage project in California is a closed loop system. It's based on a mining area, and it doesn't affect any surface hydrology. So that's currently going through licensing.
Okay, good. Julius, I have a question here. Does variable speed turbine require more maintenance than a conventional unit?
There is a small increase per the operators, long-term operators of that equipment. This is Tokyo Electric Power and the J Power. They say there is a small increase in replacing some consumable parts, such as capacitors, brushes, and so on, every 6 to 10 years. So it's not much, but a little increase, yes.
Okay, great, thanks. And then a follow-up question, Julius, about the Japanese site with the seawater, the Okinawa site. Are there any published papers related to that?
I believe they are. So if the author of that question could send me his email asking, I probably should be able to deliver some information.
Okay, great. Well, that seems to be all of the questions that we have. I want to thank all of the speakers for your contribution to the webinar. I want to thank all of the attendees for coming with your interest and asking your questions that I'm sure were relevant to everybody attending. So thanks very much. We should be following up with information on how to download a recording as well as a PDF of the slides. Thank you.
Thank you.
Thank you.